Fine. So, as I was telling, in Burdwan University graduation course, you have this astronomy part. So, you are supposed to learn about how to measure the mass of a star, the orbital time period, and all that stuff. The measurement. It is very easy, and not very easy, but you will see that probably you have also done this. You will see that using very basic physics, classical mechanics, and all that stuff, you will be able to know about the most important observable properties of the stars. So this is what astronomy is all about. Now, this astronomy also takes input from the physics, which is required to understand the celestial objects, and that is astrophysics. Okay, now this is what we will do here in masters. Astrophysics, this is the important part. So this was in graduation, this is right now. Now, as I was telling you, this particular topic, astrophysics, that means the physics of the celestial bodies, this requires input from various branches of physics. Now, one of the very old and important branch is classical mechanics. Next one is quantum mechanics. Now, you will say, sir, why is classical mechanics important? Because most of the time the density is very low. Inside the star, if the particles are very far away, you don't need to bother about the quantum behavior, right? But there can be scenarios when the density can be very high. The particles are very close. So the de Broglie wavelength becomes comparable to the distance, dimension. And then what? Then you have to use quantum mechanics. And of course, in the star, mostly they are gases, right? Plasma is also there. Now, how do we try to understand the behavior of the gas normally? One of the ways is the equation of state, right? That means we write down the pressure as function of density, temperature, composition, and many other parameters. Now, suppose one of the parameters is absent. Say pressure becomes independent of temperature, then what? Then it has consequences. Okay. Such things arise in the course of stellar evolution. When a star takes birth from the gases, then afterwards there is slow changes going on. Now, what is the driving force behind all these changes? The main driving force is nothing else. Out of the four important forces, strong, weak, electromagnetic, and gravitation, out of all these forces, the main driving force in stellar evolution, remember, is gravity. So only because of gravity, it has started forming. The star has given birth from a huge gaseous nebula only because of gravity. Why? What is the problem there? You see, inside a very big nebula, if you consider a simple gas particle, then what are the effects working on it? One is it has a thermal motion, kinetic energy, and another is there may be cluster of particles somewhere because of which there is a gravity working on. So there are basically two opposing forces. One is kinetic energy, another is gravity. Only if the gravity is strong enough to overcome the kinetic pressure, then the star becomes collapsing. Okay, out of the gaseous nebula. Now, as it collapses, so on and so forth, what happens? Density increases, and then all different types of phenomena start happening. Now, here, nuclear physics is also very important. How is nuclear physics important? So, let me ask you a question. You are sitting in the classroom right now. Okay. Just now, the air we inhaled. Okay. So, what was in the air? Lot of stuff. Along with pollution, carbon dioxide, carbon monoxide, oxygen, and all that. Okay. Let us choose one molecule particularly, carbon dioxide. Okay, one carbon dioxide molecule which we have just inhaled right now. So the question is, what was this carbon dioxide molecules 5 minutes before? It was probably still in the room. 5 years before? 5,000 years before. Where was it? How did it form? Where did it came from? You will be amazed to know that probably the same carbon molecule, okay, was inhaled by Napoleon as well. It's a possibility. In statistical mechanics, it's a possibility that what's the possibility that the oxygen you have just now inhaled, something like that, some molecule, it was inhaled by Isaac Newton. It's a possibility. But now let me not talk about it, but talk about where is it coming from. There are many possibilities. One is that after industrial revolution, there are many chemical processes during which such byproducts are produced, right? But let us now keep aside those byproducts and then ask, suppose this carbon dioxide is not a part of any man-made activity. It is not a part of any man-made activity. So the question is, how was it formed? Now inside the carbon dioxide you have carbon and oxygen, right? How was carbon formed? How was oxygen formed? Now you do know from very basic astronomy, right, that after Big Bang, what was there? Immediately, not immediately, after some time, mostly hydrogen and nothing else. So where is this gas coming from? Forget about gas. Where am I coming from? I mean, where am I? That means I, which is composed of so many elements, coming from. What is the origin of these elements? Now this is the topic. This is what nuclear physics deals with. This is the input that it gives to astrophysics. So basically, it gives you the details of the origin of the elements. How was it formed? Even as we are speaking during this lecture, still stars are being cooked inside, elements are being cooked inside stars. More and more carbon dioxide, oxygen, carbon and all that stuff are being prepared. Now the question is, number one, what is their relative abundance? How much carbon is produced, how much oxygen is produced, how much gold is produced, all that. Okay. Number two question. What is the rate of production? This is very important. Rate of production. Not just production, but rate of production is also very important. Now these are the stuff which nuclear physics will tell us. And this is actually the topic of this lecture, nuclear astrophysics. Here we will talk about this stuff only. And there are other inputs to astrophysics, say plasma astrophysics as well. Okay. And many more. I am not talking about them. But more or less this is the summary. Okay. So this is what we will be talking about in nuclear astrophysics. Mostly origin of the various elements. Basically, we would like to answer why we see, what we see, how much we see. Why is it that? Why is gold costly? Why is gold costly and not iron? Same, very basic question. Any small kid asks, right? Why is gold costly? And nothing else. We say it is very less available on earth. It is very important. So why is it less available on earth? If you ask the small child, he will say, let us go to moon. Probably it is more there. The answer is no. And why is it so? These so many whys we will try to understand. Okay.